Welcome to the Tardigrade Chronicles. I'm Rudolph. In this episode, we're going to look at evolution in how it's designed locomotion and movements on life on Earth and how we've tried to capture those in robotics. This is a really hot topic right now, as you've seen humanoid robots populating the world in various places. Robotic Olympics, robotic events, and there's been interesting examples of how we have designed robots based on humans. In this episode, though, we're going to focus on locomotion more specifically with regard to legs and wings. These are how evolution designed mobility on our planet. And of course, the evolutionary pressures that are at play in that design really resulted in quite a diverse design features of legs. From centipedes to bipeds, legs are conserved across evolution. And we'll explore that with regard to how we've built machines based on our understanding of how legs work. Similarly, those that didn't occupy just the land space developed wings. Insects' wings, bird wings. These allowed organisms and life species to populate air and fly, both in short distances as well as migratory distances over thousands of miles. This story actually also begins with an engineering feat, and that is to build sensors that could actually measure things on legs and wings of varying size and inform us as to how engineers should design and build those legs or wings. And again, these are forces. Gravity on our planet is a strong evolutionary force that helped design over time these quite amazing designs. And these forces are conserved over nature and over evolution because our gravitational field hasn't changed much over the course of evolution. And we'll look at those. Locomotion in evolution affords access to unique properties in life, access to reproductive targets, migratory breeding grounds. Finding a reproductive mate often requires locomotion. Also, predator-prey dynamics are very much involved with being able to run from a predator or to stay with a herd or a flock to be safe. All of these require locomotion. Now, man, in his evolution, invented the wheel. And so locomotion for man certainly is an interesting story because the wheel allowed man to build roads and locomote for other purposes. And we'll actually look at that because in interesting ways, it drove the design and engineering of some of the vehicles and robots that we'll discuss. So, as I said, this topic's getting news both in terms of what robots can do, and then some of the early robot companies like iRobot just announced that it has gone bankrupt. They, of course, developed the Roomba, which is the automatic vacuuming system you may have in your home. But iRobot actually started one of the first robot companies that we'll also look at and discuss. But it was the invention of these sensors that allowed us to measure these forces on legs and wings that started in the 90s, even though we started to understand how legs and wings worked for different organisms in the 1960s and even earlier. But there were some really important people who brought forward dynamic principles that helped engineers both understand and then build legged and winged robots. And those people really started to look at these force dynamics of legs, whether they were at the centipede, very small scale, or all the way up to bipeds. You may have encountered some of these videos out of the MIT Legged Lab by Mark Rabert in the 1980s and 90s. And Mark Rabert began to describe the force dynamics in those systems as a spring-loaded inverted pendulum. So think of a spring and how it bounces on the ground. Well, it actually sloshes kinetic and potential energy back and forth. So the potential energy created by the spring as it lifts off the ground is converted into kinetic energy that can be used to locomote. That spring-loaded inverted pendulum, when I first learned about it, reminded me of Tigger and Winnie the Pooh. If we all remember, Tigger used to bounce and move around Winnie the Pooh cartoons. Maybe he didn't use a spring-loaded inverted pendulum, which is the acronym called slip dynamics. But it was the same concept of using a spring-loaded force that could convert potential to kinetic energy that began the principles that we could build from. And Mark Rabert is really a giant in this field. He did go on to form a company called Boston Dynamics, which you may have also seen videos of, because Boston Dynamics, when I met them in the mid to late 90s, still had all of those systems tethered. So beautiful videos of bouncing, running machines and robots, but they were on treadmills and on tethers. We'll talk more about why the tether. It's a control issue. Not just how do you start to conserve and capture these force dynamics, but how do you control them? And we'll talk some more about that. I met Mark Rabert in the mid-late 90s, and I had the fortunate experience of challenging Mark with a very interesting problem. At the time, again, I was working for the Defense Department and national security, and we had problems with roadside bombs. Remember I said that the human invented the road, the wheel and the road, that their locomotion principles were then gathered towards as we built more and more machines, as we left the horse to build machines and cars and vehicles that can transit on roads to locomote. Well, these actually became targets. Roadside bombs, of course, not only impact many people in the Defense Department, but many civilian people, and landmines put on roads. So there was interest in understanding how could we build machines that didn't require roads? Because after all, life doesn't really run on a road. Most life uses legs or wings to transit across a variety of landscapes, some quite rough terrain. If you've ever seen some of the animals in the Rocky Mountains that climb, the goats, the mountain goats and the billy goats that climb and transit in very steep terrain. We weren't interested in that so much, but just understanding, could we build robots that captured these design principles and didn't require roads, that they could transit over rough terrain like a runner does on a path if you're a runner and you like to run outside. So this was a challenge. This was a big challenge. And I was in a position again to challenge really smart, dynamic people like Mark and say, Mark, let's build something that can run off a road that doesn't require a tether. Now, at the time, I've always been a big dog lover. I've always had dogs my entire life. Love the animals. They're just such a strong bond between humans and dogs and horses. And one breed that I was with at the time was a German short-haired pointer. My dog at that time was Laney, and Laney was a fantastic Frisbee player. Not only could Laney run through the woods at about 20-25 miles per hour over anything, I mean logs, rocks, but she could leap into the air 5 feet, catch a Frisbee, and bring it back. So I was in a position at that time in my life to say, Mark, let's build a dog. Let's build a dog that can run much like my dog, Laney. And again, I was at an agency called DARPA that allowed this kind of investment to take big challenges, fail fast, take risks. And we set about to build the first autonomous running dog. It was called Big Dog at the time, even though Laney was maybe about 55 pounds. She wasn't a huge dog, but she was incredibly agile, and that's what we were after. So this started probably a decade of building to try to capture the attributes of Laney and a dog in a platform. And in fact, you may have seen Boston Dynamics dog Spot that came out of that program. It's a yellow painted, beautiful machine that actually can do a lot of the attributes of what Laney could do, other than jump up and catch the frisbee. That's a sensor challenge. We'll talk about that perhaps in another episode. But it was a significant challenge. And so the first challenge, of course, was to capture that slip dynamics in a running robot. And of course, before we started with the dog, we actually started, as I said, with smaller species mimetics. So we built an insect, basically studied cockroaches and how they ran across rough terrain of different size terrain. So big rocks, little rocks. We could actually modulate carefully the features of these terrain and measure the force dynamics of these legs as they ran across these terrains. Turns out I still have one of these platforms here in my study, and this is one of those platforms. It was called R-Hex for robotic hexapod. You can see it has 6 legs that rotate, but also 6 legs that can capture that force dynamics. These are some elastomeric materials, rubber-like materials, that allow the legs to bounce on the ground and capture that Tigger-like motion of slip dynamics. And there are some beautiful videos of these first efforts to try to capture the slip dynamics in legged vehicles like a hexapod or a dog. Now, what was really interesting about this is this all didn't require much computation. It didn't require that you built a brain for the dog or the robotic hexapod. It really just was measuring and optimizing the force dynamics of that pogo-like motion called slip, that sloshing back and forth of kinetic and potential energy. And that really was the magic of creating what Mark showed in his first videos in the 80s and 90s on tethers, but captured for the first time in autonomous or untethered robots or vehicles. Now, Mark was an engineer. There were some significant contributions, of course, from the biology community studying animals, because these were conserved in evolution. And the department at University of California, Berkeley, the integrative biology department in the 90s, was an unbelievable trove of creativity around this topic. Bob Full really put the first papers into the literature about how a variety of animals capture these slip dynamics. And that was an important aspect as the engineers continue to build, to inform the engineers about what biology and what evolution had designed and captured in a variety of legs. Now, Bob's work also looked at a unique organism called geckos, and we'll talk about those in another episode, because Bob was not only interested in geckos locomoted on the ground, but if you've ever been in Florida or in the Southwest United States, you've seen geckos perhaps in your house climbing walls. And the interesting aspect of some legs is allowed species to leave land and get into the vertical canopies of trees, rocks, others, and how geckos stuck to walls. That turns out to be a material story we'll come back to in another episode. But Bob Full was really an important contributor to the understanding of how legs across a variety of species could contribute to these engineering builds. And in fact, Bob and a team from Michigan and a team from the Navy built that platform, that robotic hexapod that I showed you. And I mentioned that these platforms didn't require much computation or a brain, but this became more important once those slip dynamics were captured. And in fact, the central pattern generators for locomotion have been known from the neuronal community even before these machines were built. So most of the machines that were untethered that we built with the slip dynamics were still run by joysticks. And in fact, most of the humanoid robots that you see on the videos on the internet are joystick driven. And in fact, Atlas, the biped from Boston Dynamics, Spot, is mostly joystick driven. Now, there are, of course, applications for Spot, such as in security and perimeter for manufacturing sites or other things where you can program movement based on GPS. But we're distinguishing the capture of locomotion dynamics through force from the central pattern generators or the codes required to navigate or to purposely locomote, as evolution did in the context of finding a mate, finding food, avoiding a predator, or herding or flocking with animals to afford prey defense. So that came later as a second chapter of their design and build. Is now I've captured the force dynamics of these legs. They can climb stairs. There were some really very humorous videos, appearances. So Big Dog, before it was called Spot, appeared on the Colbert Show. And the most, I think, compelling demonstration that these force dynamics have been captured was if you kick the dog. Now, I'm not commending anybody to kick their dog, but this was an important experiment because in kicking, you're actually introducing a force perturbation. And the most amazing videos of what happens after that really captured what was going on, because you almost anthropomorphize this. When you see the dog getting kicked with a force perturbation, it actually scrambles its legs to maintain its body position, to maintain its upright body position, entirely by managing and optimizing the forces of the legs. It didn't require a central pattern generator or a brain or a computational central feature to allow you to observe what evolution had designed, is that these legs really afforded not only locomotion but stability. So you're not going to pop a wheel. You're not going to break a track on a tank. You're going to have a very stable, dynamic system that can transit over rough terrain. And that was, of course, the defense applications. Now Spot's out there in the world doing lots of things. Spot's been in parades, Spot's security, Spot's in warehouses helping move inventory around. I mean, the whole world of robotics is still seeking applications that are still in front of us. But this stability of legs was really important. There was another chapter in locomotion that's important to bring forward that is even less mature in robotics, but important in the context of capturing evolutionary dynamics. And that's how do wings work? Now, wings, of course, have a variety of features and designs across evolution. And we're going to focus on flapping wings more than the sort of wing dynamics of just sort of floating, if you will, or gliding. Wings have a lot of aerodynamics that allow a number of features. But it wasn't until around the year 2000 that we understood how a fly got off the ground. What were the force dynamics that allowed a fly or a bee to lift off a surface? It was, when I heard this, I was really quite shocked that we didn't understand this yet. And again, it was a problem associated with engineering. We didn't have the sensors to measure the force dynamics of an insect wing. Enter Michael Dickinson, also at that UC Berkeley Integrated Biology Department, now at Caltech. Mike Dickinson, in that period of time, defined for the first time how wing rotational force dynamics result in the ability of liftoff of a small winged living system. Now, once that was captured, again, much like in the legged system, we could build machines and flapping autonomous vehicles that worked like flapping wings in life. And that story was interesting. I happen to be a tennis player, and it turns out that the force dynamics of a rotational insect wing are much like a topspin tennis shot. So if you're a tennis player, you know that in a topspin motion, when you bring your racket up quite fast across the ball, it lifts the ball up and gives it that top spin. Of course, when it hits the ground, it has a little bit of a jump. But that force you're creating in that top spin motion is very much like the forces at play in an insect wing at much higher frequencies. And the experimental designs that were required to measure these were really amazing. I mean, if you could imagine placing a force sensor on an insect wing, putting it into a small chamber and measuring these force dynamics as this fly decided to land, decided to lift off, and did different dynamic features in flight, thus allowing the engineers for the first time to build flapping wing autonomous vehicles. Now, there's lots of reasons to do that. They've been seen in movies, but they're also being used in reality. Now there are some flapping drones. So all of this enabled the engineers to really move forward and build systems that really captured those force dynamics. Now, I mentioned that these systems didn't have significant computational power in the sense that they had brains deciding what to do with their locomotion. They were really just to capture the force dynamics of these legs and wings. But obviously, in order to build a robot with some application, that purposeful computation, and whether it's navigation, whether it's a task that you're asking a robot to do with its arms or its legs, or a winged vehicle, is an entirely different kind of engineering challenge. And so we're really focused on the force dynamics of locomotion and how they were captured. But as you can see in the world of robots today, they are constrained by that higher level computation, higher level behavior that can be captured and faithfully and rigorously put into engineering systems designed. And that's why you see on the internet recently, the Russians brought out a humanoid and it fell over. That one didn't particularly capture a lot of force dynamics, but a lot of the failures you're seeing in robots are not based on something that is as simple as the force dynamics, but the more challenging problems of how do you get a robot to take higher level tasks. And there are certain degrees of freedom in some of these built systems that can't be captured yet with a software system or an understanding of how robots will function. What will be their purpose in locomotion? Now, of course, we're in an era of AI, and robots are learning very differently, much the way we're learning very differently. And so there's going to be a very rapid evolution, if you will, of robotic behavior now that we have a much larger way of looking at perspective in AI, looking at large language models that can look across a variety of robotic learnings, capture those, embed those in software systems where we'll see more and more functionality, purposeful movement. And that's a really exciting time for the robotic community. When I was at DARPA, they went on to robotic challenges, a number of which, ended up with a lot of bloopers about this purposeful function of robots. But what was so important about the chapter of this time in that I've been describing in this episode is that over the last decade or two, we captured the force dynamics of how evolution designed and built legs and wings. And that will really come to fruition once we add this more purposeful computation, artificial intelligence learning of robots' purposeful movement. And so it's a really exciting time for robotics a really exciting time to impart these evolutionary principles into new designs, and I'm glad I had a chance to share it with you. I'm Alan Rudolph. Thank you for joining me on the Tardigrade Chronicles.